In this video, we discuss the use of pilot points. Pilot points are a convenient means of parameterizing a groundwater or other models with a spatial model domain. They allow us to use many parameters in solving the inverse problem of model calibration. Before we talk about the details of pilot points, let's remind ourselves of some issues that we talked about in other videos. In particular, let's remind ourselves of what are the benefits of undertaking highly parameterized inversion, that is, using many parameters in the inversion process, that is model calibration. We discussed the fact that ideally that quest for uniqueness, which is model calibration, should lead us to a minimum error variance solution of an inverse problem. We don't get the correct parameter field, we get a parameter field whose potential for wrongness has been minimized if we do our regularization properly. And that happens better if we have many parameters at our disposal. Another advantage is that we leave open room for surprises. We may find that heterogeneity arises in unexpected places within our model domain. And this is important to know because we have the ability then to use calibration as a data interpolation, a data interpretation mechanism. We find out a little bit about what's under the ground through history matching. And by having parameters at all parts of the model domain lying in wait to receive information about what may be under the ground, that any heterogeneity that requires expression can be expressed by the appropriate pilot points. Also, as we've also discussed, using lots of parameters gives us the ability to analyze the uncertainties of predictions made by a model. If a prediction depends on parameter components or parameter combinations that are inestimable through the calibration process, then the uncertainties of those predictions will not be reduced much at all through the history matching process. It's the parameters that we can't estimate that are just as important as those we can. So having lots of parameters allows us to capture what information is available and then to express through quantified predictive uncertainty the ramifications of not having enough information available to make accurate predictions of certain aspects of the future behavior of a system. Groundwater parameterization, groundwater model parameterization has some extra constraints as well. Yes, we'd like to have a lot of parameters for the reasons that we just outlined. However, normally when we're calibrating a groundwater model, we are calculating the Jacobian matrix on which basis we estimate parameters using finite parameter differences. That is, we undertake one model run for each parameter, vary the parameter incrementally, look at the difference in model outputs, calculate that difference, divide it by the difference in parameters to get an approximation to our derivative. Now, if we have too many parameters, individual parameters become insensitive, and that finite differencing process breaks down because we're taking two numbers, one from another, which are very close together. And because of that, we lose significant figures. Therefore, the finite difference derivatives calculation process becomes compromised. Pilot points, therefore, allows us to occupy a kind of a middle ground. We can have a lot of parameters for the advantages that we've just spoken about, but we don't have so many parameters that our ability to calculate finite difference derivatives is lost. Now let's look at the principle of operation of pilot points. Pilot points are ascribed locations in space. So each pilot point is given an x and y coordinate, or for three-dimensional pilot points is given an x, y and z coordinate. So pilot points are distributed throughout a model domain. Now, the process of calibrating a model or of parameterizing a model using pilot points is actually a two-step process. Firstly, PEST assigns values to the pilot points. That's the first step. The second step is that interpolation takes place from those pilot points to the model grid or mesh. That grid can be structured or it can be unstructured. It doesn't matter. Now, just because we're using pilot points doesn't mean we can't also use zones. We can ascribe pilot points to different zones. So in this picture, the brown pilot points are ascribed to this upper zone. The blue pilot points are ascribed to the lower zone. Interpolation doesn't cross zone boundaries, so cells in this part of the grid are not informed by pilot points in the other zone if we tell the interpolation process that this is how it's done. Interpolation can take place in different ways in different zones, so they can be completely independent. And by using pilot points in combination with zones in this manner, we are effectively telling the inversion process that, if it can, introduce heterogeneity at the zone boundaries. If further heterogeneity must be introduced to allow a good fit to be attained between model outputs and the calibration data set, then the inversion process can introduce that heterogeneity within the individual zones. So this gives us even more flexibility in calibrating the model. Some other features of pilot points, as I just mentioned, they can be two-dimensional or three-dimensional. The software supplied with PEST allows a variety of methods to be used for interpolation from pilot points to a model grid or mesh. Any type of parameter can be associated with pilot points. We can associate hydraulic conductivity, porosity, storage coefficient, inelastic storage. It doesn't matter. The pilot point is independent of the parameter type. These parameters can even be multipliers or numbers that we add to an existing parameter field with which a model is endowed. This allows the calibration process to be very flexible indeed, so that PEST then can assign multipliers, for example, to an existing parameter field and told to modify that field as it needs to so that model outputs are well matched to members of the calibration dataset. When we're using pilot points then, as we just said, parameterization of the model becomes a two-step process. So the model must be comprised not just of the simulator. A program must run in front of the simulator to do the interpolation from pilot points to the model grid. So the model must actually be encapsulated in a batch file on a Windows system or a script file on a Linux system. So here's a picture of PEST with its non-intrusive interface with the model. Recall that PEST writes model input files using templates of those files. It reads numbers from model output files using instruction files. Now, however, the model that PEST runs includes not just the simulator, but the program in front of the simulator which does the interpolation. Proc is the preferred way of doing this. However, it's not the only member of the PEST suite which allows you to do this. It is the latest member and the best member for doing this. We'll talk about it soon. Proc stands for Parameter List Processor. So PEST then has to write input files for PL-Proc using template files. PL-Proc writes input files for the model. And in doing so, it attempts to maintain that same non-intrusive interface with the model that PEST uses. PL-Proc actually uses template files to write model input files. But these template files are a little more sophisticated than the template files which PEST uses. Because after interpolation, PL-Proc must write thousands of numbers to model input files, whole arrays of parameter values. Those template files which PL-Proc uses can include so-called embedded function, which allows transfer of those hundreds of thousands of numbers to take place fairly easily. And the complexity of the template files which it uses to write model input files does not have to be too great. So now let's say a few words about PL-Proc. PL-Proc, as stated before, stands for Parameter List Processor. PL-Proc can undertake kriging from pilot points to a model grid using a variety of different mechanisms. The most used are kriging and radial basis functions, but it can also use inverse power of distance. It can interpolate from pilot points to a model grid. It can interpolate from a model grid to pilot points. It's very flexible in the way that it applies its interpolation schemes. For example, you can control the algorithm used for interpolation on a pilot point by pilot point basis. And we'll just talk about that shortly. Horizontal anisotropy used in the interpolation can vary from place to place, and in fact so can vertical anisotropy if we're using three-dimensional pilot points. Upper bounds can be set on a pilot point by pilot point basis, or they can be set on a cell by cell basis. It'll interpolate to a regular grid or an unstructured grid. And not only can it undertake interpolation, it can also undertake arbitrary mathematical operations between pilot points, all the values assigned to pilot points, and also the values after interpolation assigned to the model grid or mesh. So it does more than just interpolation. We'll see some examples soon. It can also do mathematical operations which makes the parameterization scheme and the calibration scheme as flexible as possible. Let's talk just for a moment about kriging and radial basis functions. Kriging as an interpolator has certain advantages which make it very attractive. It's numerically quite rapid. The values are honoured at the pilot points, so the interpolated values at the locations of the pilot points are the same as the values ascribed to the pilot points themselves. It doesn't tend to be too prone to undershooting or overshooting, especially if we use an exponential variogram. It also has some nice features with simple kriging, which we'll talk about shortly. The mean value supplied with simple kriging stabilizes extrapolation if we have to undertake extrapolation and not just interpolation. However, it's not the perfect interpolator. Interpolated parameter fields can sometimes appear a little bit blotchy with bullseyes at the pilot points. Sometimes there can be problems with differential spatial densities of pilot points, though with functionality supplied with PL-Proc, this can mostly be eliminated. If you're not careful, there can sometimes be a paintbrush effect, artificial discontinuities in an interpolated parameter field. This can happen if your search radius used in pilot point interpolation is not larger, considerably larger than the range of the variogram on which pilot point interpolation is based. That way, as pilot points move in and out of the search radius, there can be artificial discontinuities in the interpolated parameter field. Radial basis functions eliminates those problems, but it has a few of its own. It honours the values at pilot points. The interpolated parameter fields, they're not as blotchy, we don't have bullseyes, but sometimes they're just a little bit too smooth and a little bit too wavy and can look a little bit unrealistic. Also, as with pilot points, sometimes we can encounter problems where we have as with kriging, sometimes we can encounter problems if we have differential densities of pilot points in different parts of the model domain. But that can be largely fixed up in ways we'll talk about shortly. One problem, however, is that because of the nature of this interpolation, the highest and lowest values ascribed to the interpolated parameter field tend to occur between the pilot points rather than at the pilot points. Now, when the highest and lowest values are at the pilot points, as they are with kriging, that means if we apply bounds to parameters in a PEST control file, those bounds effectively apply to the interpolated parameter field and not just the pilot points. However, if the highest and lower values of the interpolated parameter field happen between the pilot points, then the bounds we apply in a PEST control file actually may be superseded by the bounds after interpolation. We will have higher or lower values in that interpolated parameter field than the bounds we apply in the PEST control file. And this may be a little bit of a pain on some occasions. Because PL-Proc is so flexible in what it does, the user instructs PL-Proc what to do using a script, a kind of programming language. This can be a little bit difficult to use, but it's all described in the PL-Proc manual, and this is actually the cost of flexibility. As stated, not only can we interpolate, we can do mathematical operations between pilot point arrays and model grid arrays, and do things even a little more complicated than that. And so we can kind of build a parameter field for a model through a series of steps. These steps are expressed through the functions that we can call when we run PL-Proc. So a file has to be written with this set of instructions, and this file can get rather lengthy in complicated situations. However, this is what gives PL-Proc the ability that it needs to do realistic, useful interpolation and parameterization of a model domain, so that the inversion process conducted by PEST can make maximum use of field data to parameterize a model. So let's spend a little bit of time looking at what happens when we have differential densities of pilot points. And this is something that can occur quite often in parameterizing a model domain. There are a number of options available, two of which I'll discuss now. Option 1 is two-stage interpolation. Suppose that I have a model domain and that in the first stage of interpolation I give it a background parameter field. I interpolate from those red pilot points to the model domain. And these pilot points are placed on a regular grid at a considerable distance apart. Note from this picture, by the way, that pilot points ascribed to a model domain or a zone don't actually have to lie within that model domain or within that zone. They can lie outside of it and still interpolate to it. And that's often recommended practice, actually. We don't want to extrapolate, we want to interpolate. And we don't extrapolate where some pilot points actually lie outside the model domain. Suppose in this case that there are two areas of considerable interest within that model domain. There may be more data available in those two areas that comprise the calibration data set. We may be interested in detailed predictions in these areas. If we're using an unstructured grid, the grid may have greater density within these areas. We can then introduce a secondary set of pilot points, in this case coloured blue, and in this case on a much finer grid. So interpolation here becomes a two-step process. This secondary set of pilot points can actually carry multipliers which perturb the background parameter field interpolated from the red pilot points. And to undertake that interpolation, we use simple kriging with a mean of 1. Now, by using simple kriging with a mean of 1, this says that as the points to which we undertake the interpolation move away from where these pilot points are, we fade back to a mean of 1. So we can actually do extrapolation here, but the extrapolation is very stable. We multiply the background parameter field by the multipliers interpolated from these pilot points to the grid. So we have grid multiplying grid, but the multiplier value fades back to the mean of 1 as we move away from these areas where the action is, so that we've got then a situation like this. Background parameter field, multiplier parameter field fading back to 1, interpolation taking place using simple kriging. And that allows us to accommodate in a seamless way much greater parameterization density in this area than in the background area. Background interpolation can take place in whatever way we like, ordinary kriging or radial basis functions. Another way of dealing with the situation where we've got variable densities of pilot points is to invoke some special PL-Proc functions which are designed specifically to handle that situation. For kriging, we can use this function, calc kriging factors auto 2D. For radial basis functions, we have RBF interpolate 2D. In both cases, the mathematical operation which underpins the interpolation adjusts itself automatically to the local pilot point density. So if, for example, we're using kriging and in places where the pilot points are close together, the range of the variogram on which basis interpolation takes place is small. Where the pilot points are further apart, the range of the variogram on which basis interpolation takes place is greater, and this is all done automatically behind the scenes. For radial basis functions, a similar thing applies. The variables which govern the wavelength of those radial basis functions adjusts itself automatically in accordance with local pilot point density. And we can get even more complicated than this. If we want to have some directionality incorporated into the interpolation process, that is, if we would like heterogeneity to arise in certain directions rather than others, we can ascribe anisotropy to the variogram or the radial basis function. And that anisotropy can vary from place to place within the model domain if we wish it to reflect differences of geology which may prevail in different parts of that model domain. Here's an example. Notice how far apart the pilot points are in this part of the model domain and how close they are in this part. We can see how we can easily accommodate the broader interpolation here, the smaller, the more greater wavelengths of the changes of parameter value here, while accommodating the much smaller wavelength of changes of parameter value in this part of the model domain, all in a seamless fashion. Another layer of the same model. Once again, we can have more small-scale detail heterogeneity in some places and broader scale heterogeneity in other places, easily adapting itself to the differential densities of the pilot points from which interpolation takes place. This can be extended to even more complex situations. There's a function in Proc which allows us to accommodate alluvial valleys. Here's an example of an alluvial valley, and is typical of such valleys. They change their direction as we move down the valley. Proc allows the anisotropy of the interpolation to follow the valley. So here, for example, we use a regular array of pilot points, but sticking close to the valley. This particular function in Proc allows, as I just said, the anisotropy associated with the interpolation to follow the valley. We expect the heterogeneity to be elongate in the direction of the valley in an alluvial system just through the nature of deposition in that system. And of course, as the valley changes its bearing, so too must the direction of anisotropy that allows the heterogeneity to be elongate in the direction of the valley. And this can all be done automatically using that special Proc function. And there's a close-up of part of the valley. Here's another example of creative use of Proc. In this case, the model is actually a geothermal model. This is a tough model. We've got a three-dimensional model domain, in this case a rectangular prism with the top surface following the topography of the land. This is a couple of kilometers in depth. This is divided into three broad zones. This is the central part of the geothermal system and the peripheral parts. There's the model grid, and there are my pilot points. In this case, it was considered appropriate to arrange these pilot points in a number of layers, in this case 4 layers, and to separate the pilot points into different zones because of the different nature of the geology in each one of these zones. Parameterization of the model domain took place in a number of steps. Firstly, two-dimensional interpolation was undertaken in each one of those layers, in each one of those zones. So interpolation here took place independently from interpolation here, independently from interpolation here, independently from interpolation here, etc. That was step 1. Step 2 was to undertake interpolation in the vertical direction between the layers that were informed by horizontal interpolation during the previous step. So we ended up with this disposition of log permeability, coloured according to the log of permeability in this figure. Yet another example of sophisticated parameterization of a model domain, done in an endeavour to make maximum use of geological knowledge at the same time as obtaining a good fit with a comprehensive calibration data set. So this is the model domain, and my colleagues in this case used or emplaced their pilot points in a regular grid. That's the grid that was used in layers 1 to 4. This is the grid that was used in layer 5. The calibration data set consisted of heads in a number of observation wells and also subsidence. Each layer of that model domain was assigned many parameters: hydraulic conductivity, but also horizontal anisotropy, vertical conductivity, specific yield, elastic storage, inelastic storage, and critical head. Now, these different parameters ascribed to the same layers are not independent. After all, they do describe the same rock types. And my colleagues felt it important, and I think this makes sense, to accommodate the fact that there should be relationships between these parameters. Now, how one does this is a matter of taste. My colleagues decided to do it in the following manner. Based on information that they had at hand through characterization of that site, through field and laboratory measurements, they established regression relationships between so-called secondary parameters, that is, these ones here, and KH. So parameterization of this model domain then became a multi-step process. It was posited that these relationships existed. The variables which governed the exact nature of these regression lines were calibration adjustable. They were adjusted during the calibration process, but preferred values were supplied for those variables. So the first thing which PEST did then was to interpolate from KH pilot points. Well, values were assigned to pilot, KH values were assigned to pilot points, and these were interpolated. This is what Proc did. So values were assigned to pilot points, KH values. These were interpolated to all cells of the model domain. Then those regression equations were implemented, and at every cell in the model domain, values were ascribed to these second parameters using those regression equations. But of course, those regression equations aren't exact. They're kind of suggestions of the nature of the relationship between these parameters that makes sense based on what had been observed through site characterization. Then, for each one of these parameter types in each layer, multipliers were ascribed to the same set of pilot points that we saw previously. PEST then adjusted these multipliers such that we could perturb the KV, SY, SE, SC value assigned to each cell in the model domain. They could be perturbed through multiplication by the minimum amount required to fit the calibration data set. Tikhonov regularization was employed during the inversion process, as it should be, so that perturbations from these regression relationships were only as much as was required to allow a good fit to be attained with the calibration data set. So KH was estimated, Values for secondary parameters calculated on a cell-by-cell basis using multiplier arrays interpolated from pilot points. Those secondary parameters could be adjusted to fit the calibration data set. In doing so, maximum respect was paid for expert knowledge, but at the end of the day, a good fit was attained with the calibration data set. Parameter fields appeared to be quite reasonable, and good fits were attained. I'd now like to say a few words about where we actually put the pilot points. Now, there's no one way to do this, but I'll suggest a method that I use lately when I've been building models. The first question is regular or irregular. We've seen examples previously in this video about regular placement of pilot points. I tend to place them irregularly these days. The reason is because normally I'd like to use as many pilot points as I can, but it makes sense to use those pilot points economically, which implies that where I have information from the calibration data set, that's where I should put more pilot points, have a higher pilot point density than in those parts of the model domain in which I don't have information. There I can be more frugal. And if I've got a multi-layer model and I have different sets of pilot points for each layer, and each one of those pilot points is used for interpolation of different parameters, then I am going to have to be economical about how I emplace them, because I could end up using too many pilot points for the computing resources I've got, and then calculation of the Jacobian matrix could become very numerically intensive. So this is the line of thinking that I normally employ when I'm emplacing pilot points in one layer of a model domain. The same logic as this can apply to multi-layer models. Just apply that logic to within each layer of each multi-layer model, of a multi-layer model. So suppose we've got a situation here where we've got a fixed boundary down the bottom of the system. Here are our observation wells where we're measuring heads or concentrations, whatever. There's less data around the side of the model domain. And let's assume that groundwater flows in that direction. So the first thing I do, as I just said, is to propose a budget. How many pilot points am I going to use in parameterizing this model? But in particular, how many pilot points am I going to use for this layer? Once I've decided that, I then start the process of pilot point emplacement. So first, I place pilot points in that part of the model domain where they're needed most. That is, where the data is. Always keeping in mind that when I've finished putting pilot points into this layer, I want there to be a certain number that I've already decided. I tend to place pilot points between wells rather than on top of them. The information contained in head measurements, in particular differences of head measurements between wells, tends to inform us of the hydraulic conductivity between the wells, so that's the best place to put the pilot points, at least for pilot points that represent hydraulic conductivity. Not so necessarily for specific yield or storage, but I tend to use the same pilot points for all the different parameter types in a particular model layer, though that's far from essential. Anyway, once I've put in the high spatial density pilot points, I then add more pilot points between this first row of observation wells and the outflow boundary. These are needed so we can get the right hydraulic conductivities in this area to give us the right heads at this first row of observation wells. Then I will add pilot points to the rest of the model domain. I'll attempt to aim for some minimum pilot point density. I don't want there to be big holes in the pilot points array. And I will always try to place pilot points at or just outside the model boundary. We don't want to extrapolate, we want to interpolate. So some minimum density of pilot points through here with the final row of pilot points right at or even outside the boundary makes sense. And then I will use one of those Proc functions that we discussed previously. I normally use this function these days to undertake the interpolation from the pilot points to the model grid, this accommodating the fact that I have differential densities, spatial densities of pilot points in different parts of the model domain. So the next question is, how do we regularize our pilot point parameters? That is, how do we incorporate Tikhonov regularization into an inversion process in which parameterization is at least partially based on pilot points? There are a number of options that are available through the PEST utility support suite. We'll just talk about two. One of these is preferred difference regularization. So here's my model domain once again, and there are my pilot points. This is just one layer of the model domain. Now, for this particular layer, I formulate preferred difference regularization by adding a number of prior information equations for each pilot point, specifying that the value ascribed to the pilot point minus the value ascribed to the neighboring pilot point is 0. So what I'm effectively saying here is preferred homogeneity. Each pilot point is linked to each one of its neighbors by a prior information equation expressing the fact that the preferred value for the difference between the values associated with the pilot points is 0. Now, if multiple parameters are associated with the same set of pilot points, of course these equations must be added for all of these parameter types. So this is a methodology, and this is easily implemented with the PPK-Reg, PPK-Reg1 and GenReg utilities from the PEST Groundwater utility suite. The advantages of this method are that there's something conceptually nice about it. We're saying that this model domain is uniform, or at least this layer within the model domain has uniform values for this particular parameter type, unless data within the calibration data set says to the contrary. And because we're using Tikhonov regularization, we are saying that only the minimum amount of heterogeneity should be introduced to the model domain as that which is required to fit the calibration data set. So that often makes sense. There are a few problems, however. Where parameter numbers are large, the number of prior information equations expressing these preferred homogeneity relationships becomes even larger because we have to associate a number of equations with each pilot point. And this can slow down the inversion process. It can slow down handling of that large Jacobian matrix. Another problem is just going back a couple of slides, we tend to make the weight applied to this prior information equation greater than the weight applied to that prior information equation because we want to enforce homogeneity more strongly for pilot points which are closer together. But how much greater should this weight be than that weight? And a further problem is, what do we do between layers? So we're asking for preferred homogeneity within one layer, but then if we've got a multi-layer model, what do we ask for to regularize parameter values in one layer to those in the underlying or overlying layer? Recall from another slideshow, another video, that Tikhonov regularization should ideally provide a fallback position for all parameters. Homogeneity is a good fallback position, but it's only being applied on a layer-by-layer basis. Entire layers can still vary up and down, and they're not being actually regularized with respect to each other. So this leaves some gaps in the preferred value status of parameters that Tikhonov regularization seeks to apply. Another option which gets around these problems is preferred value regularization. And this is the regularization that I use mostly myself these days. So here again is our model domain. And for each one of these pilot points, I assign one equation, one prior information equation, which gives a preferred value for that pilot point. So each pilot point has its own individual fallback position. Now, then, that means that I only introduce one equation for each one of these pilot points. Now we can get sophisticated here. We could estimate a value for the entire layer, and these pilot points could be multipliers on that value. And as multipliers, they can have a preferred value of 1, and that's kind of a way of introducing preferred homogeneity. Or these pilot points could have different preferred values. We can do things as flexibly as we like. But the point here is that each pilot point is accompanied by one prior information equation specifying the fallback value for that pilot point. Now this gets over the problem of what happens between different layers and between different parameter types. Every parameter type ascribed to every pilot point has its own individual fallback position. Now, prior information equations which provide this fallback position can be easily added to a PEST control file using the add-reg1 utility from the PEST suite. So it's very easy to implement. The add-reg1 utility provides a preferred value for each pilot point, for each parameter in a PEST control file, equal to its initial value. But then we have to take another step. So add-reg1 adds a prior information equation for each pilot point. For different parameter types, it puts those prior information equations in different observation groups. We should then provide a covariance matrix for each one of those observation groups. Recall what we said about Tikhonov regularization in another slideshow. Not only should we provide a fallback position for every parameter, we should also provide the means in which departures from that fallback position should arise. And that's achieved by providing a covariance matrix for each group of pilot point parameters for each group of prior information equations describing pilot point parameters of the one type in the one layer. So where does this covariance matrix then come from? Well, utilities provided with the groundwater data utilities give us the ability to build these covariance matrices. They can be based on a variogram, or they can be more sophisticated than that. They can be based on a spatially varying variogram. So if, for example, we have large density of pilot points in one part of a model domain and a smaller density of pilot points in another part of the model domain, the range of the variogram can vary between those different parts of the model domain. We can have a small range for the variogram where pilot points are close together, because the fact that they're close together implies that heterogeneity may arise on a smaller scale. This is where we have information. We're putting pilot points in areas where there's high information density in anticipation of the fact that heterogeneity will rise on that scale. Further out in the model domain, where there are no boreholes, where there is no information, pilot points are placed more sparsely. We don't expect to see heterogeneity arise on a small scale in those parts of the model domain. And if we don't have information in those parts of the model domain, and we don't have any important predictions to make in that part of the model domain, then having a large range for the variogram on which basis we construct the covariance matrix in those parts of the model domain allows heterogeneity to arise on a spatial scale that's commensurate with the local pilot point density. And that mechanism of covariance matrix construction is available through these two utilities. Recall again the precepts of Tikhonov regularization. There must be a fallback position for every parameter. That's provided through the prior information equations that give a preferred value for every parameter. Tikhonov regularization must also specify the manner in which we would like departures from that fallback position to occur. That's specified through the covariance matrices that we supply for each group of prior information equations that pertains to the pilot points for a certain parameter type in a certain layer. So if we have 10 layers and each of those layers has pilot points for two sets of parameters, we will supply 20 covariance matrices. Now those 20 covariance matrices may be the same matrix if the pilot point disposition is the same in every layer for both parameter types. So this isn't as complicated as it may first appear. The advantages of this approach to regularization, the preferred value approach to regularization, is that it's relatively easy to do. Add reg 1 puts in the prior information equations. The utilities that we just saw allow us to build the covariance matrix. It gets rid of problems associated with regularizing parameter values between layers. It can be used just as easily for 2- and 3-dimensional pilot points. It can be used just as easily for different parameter types, whether they pertain to a hydraulic property such as hydraulic conductivity, or whether they pertain to a multiplier on hydraulic conductivities or any other parameter type. Yes, the disadvantage is having to build that covariance matrix, but that's not too hard, really. Okay, let's look at a couple of examples. First, a not so good example. Now, this is a fairly disgusting parameter field for a calibrated model. You can see exactly where the pilot points are, marked by these little blotches, these little bullseyes spread throughout the model domain. Now, the calibration process didn't do a bad job of defining where more and less conductive areas were. However, superimposed on these broad scale hydraulic property fields are these blotches, positive and negative blotches. So why did this happen? Well, two reasons. Recall from another video that when we use Tikhonov regularization, we supply a target measurement objective function. If that target measurement objective function is set too low, then we can overfit. And that's what happened here. But probably the main reason is failure to use a covariance matrix in conjunction with preferred value regularization. If we don't use a covariance matrix, what we're effectively saying is that every pilot point can act independently of every other pilot point to get a locally good fit with a calibration data set. But that's often not what we want. If heterogeneity arises, it needs to be a little bit more spread out than that. That's not necessarily how so we end up with a parameter field that looks a lot better, that looks smoother if we use a covariance matrix along with the preferred value prior information equations. And that smoother field isn't necessarily realistic because geology is complicated, but it's much more in tune with what we seek through the calibration process, which, you should remember, is the minimum error variance solution to the inverse problem, the parameter field of minimum error variance. Not because it's right, because we've minimized our potential for wrongness. This parameter field does not look like, to me, the parameter field of minimum error variance. It's too blotchy, too unrealistic. Now let's look at a good example. This was done by a colleague of mine who was modeling the groundwater flow in the vicinity of an open cut pit. So there's the pit, and the colouring here is according to the log of the hydraulic conductivity inferred through the calibration process. My colleague used 3 sets of pilot points. Near the pit, he used 3-dimensional pilot points which acted as multipliers on a regional parameter field informed by 2-dimensional pilot points. A third set of pilot points was ascribed to faults which pervaded this particular area. 2 pilot points were assigned to each fault. So collectively, 3 sets of pilot points then were used in conjunction with preferred value regularization to parameterize this model domain. There they all are together. And here are some sections through the model domain, again coloured according to the log of the inferred horizontal hydraulic conductivity. Some more pictures of the dispositions of the pilot points and of the faults. ModFlow USG was the model in this case. And relatively good fits were obtained between model outputs and the calibration data set. Finally, after speaking about what calibration can achieve, I'd now like to finish by saying something about what it can't achieve. So, this is a synthetic case. I've got a rectangular model domain, inflow at the top of the domain, fixed head at the bottom. I'm calibrating a model using the heads in 12 wells, steady state calibration. I'm releasing a particle that flows to the bottom of the system, but we're not concentrating on that, we're concentrating on the parameter fields in this discussion. The model domain is homogeneous with a hydraulic conductivity of 1 meter a day, except for the fact that I insert a fault or a dike into that model domain. A fault has a hydraulic conductivity that's 10 meters a day, it's conductive. A dike has a hydraulic conductivity that's 0.1 meters a day, it is resistive. And I'm going to look at 3 orientations of the dike and the fault. My parameterization device is pilot points. I have many of them, and I'm asking the question, can I see that fault or a dike through calibration of that model against 12 heads? Firstly, I'm going to do this by applying all the rules that we just talked about. I'm going to use preferred value regularization, accompanied by a covariance matrix based on a variogram with a range, well, an A value of an exponential variogram, that's about 1/3 of the range of 200 meters. On the left is reality, synthetic reality. On the right is what emerges from the calibration process. So here we have our fault, our conductive fault. That's in a homogeneous, in a uniform homogeneous background material. That's what it is, that's what it looks like. So I don't see it as a fault, I see it as more spread out heterogeneity. After all, through Tikhonov regularization, that's what I've asked for. I get a perfect fit with those 12 heads. This is a synthetic case. There is no noise associated with the calibration data set. I'm entitled to get a perfect fit. I see the existence of the fault, but I don't see it as a fault. I see it more spread out. As I said, that's what I asked for through my preferred value regularization, accompanied by that particular covariance matrix. When I orient that fault at 45 degrees, not only is it very difficult to see through the calibration process, but the small amount of spread out heterogeneity that does arise is oriented at 90 degrees to the actual heterogeneity. Once again, I get a perfect fit with the heads. Now, this just tells us about the non-uniqueness of the calibration process. The 12 head measurements in 12 wells does not have much information about hydraulic conductivity detail, and this is the result, compounded by the fact that I haven't asked the inversion process to look for this specifically. I've asked it to look for heterogeneity that's in accordance with the exponential variogram that we looked at before. A conductor that's perpendicular to a flow field is invisible. A resistor that's parallel to a flow field is invisible. At 45 degrees, I can detect that dike, not as a dike, but as a spread out lump of resistive material. Again, that's what I asked for. There are many different ways to fit that calibration data set well. I got what I asked for. Non-uniqueness of the inverse problem can express this in many different ways depending on how I regularize. The same applies when the resistor is perpendicular to the flow field. It's visible not as an elongate resistor but as a circular blob. Now let me recalibrate that model using the same pilot points, but this time introducing nonlinear regularization, which is new to the PEST suite. In doing this, I say, I know there's heterogeneity there, and I expect it to be elongate. I tell the inversion process through this nonlinear regularization that if something's conductive, let it be elongate in a certain direction, and I'm pretending I know the direction from geological considerations. So for the case of the 45-degree fault, for example, I'm saying if there's indications in the calibrated parameter field that things are conductive, let that conductivity be linear, be elongate at 45 degrees. So I'm pretending I know something. I'm pretending that I know what to look for. What happens then? So here's reality. Here's what I got before. And yes, what emerges from the calibration process does better reflect the source of the signal that appears in those 12 wells. Pilot points, of course, cannot represent a feature like this, but because I have many pilot points, they don't do a bad job of representing the elongate nature of that feature. This situation remains almost just as sad. It is very difficult to see this fault oriented at 45 degrees to the flow field. At least what I'm seeing here doesn't tell me it's oriented in the opposite direction, and I do get some signs of intense conductivity, but it's not connected. And I have little blobs of resistive material here as well. Still getting a perfect fit with my 12 heads. A conductive feature perpendicular to a flow field is still invisible, as is a resistive feature parallel to a flow field. I do a better job of seeing the elongate nature of this, but I don't see it exactly as it is. Something is introduced here which is not reflected in reality, but it does appear to be more elongate. But the fact that it's not aligned with the grid of pilot points makes representation of this feature using a pilot point parameter field quite challenging. As a result, I see elongation, but elongation in two different places rather than one. Here, this isn't too bad. The fault's in the wrong place, but that's not necessarily bad because there's no information really to say where this fault is given the disposition of these 12 head measurements. So what can we conclude? Pilot points work up to a point. They are a powerful parameterization device when used in conjunction with Tikhonov regularization. They give us the many parameters that we need to solve an inverse problem of model calibration and achieve something approaching a minimum error variance solution to that problem, when accompanied by appropriate Tikhonov regularization. However, it's the inverse problem, solution of that inverse problem is always going to be limited by the non-uniqueness of that problem, regardless of our parameterization device. Pilot points are always going to have difficulty representing structural features such as faults or dikes. And they'll certainly won't see a fault or a dike as a fault or a dike in a calibrated parameter field if we use Tikhonov regularization based on a variogram. But then again, if we don't know exactly what to look for, we don't have the ability to formulate even nonlinear Tikhonov regularization to look for it, so we probably won't see it as it is. The heterogeneity that's manifested in a calibrated groundwater model may indeed indicate that there is heterogeneity in the subsurface, but it may be a fairly poor representation of the exact nature of that heterogeneity. And that is just an outcome of the non-uniqueness of the inverse problem that we face when we're calibrating a groundwater model.